What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Section 4, Graphs of Logarithmic Functions. Let's do it. So question 1 says the inverse of every logarithmic function is an exponential function and vice versa. What does this tell us about the relationship? So between the coordinates of the points on the graph. So let's say we have an exponential function f of x, and let's say the coordinate is -7, comma 4. If we take the logarithmic, which would be the inverse, right? Let's just call it g of x. Let's say g of x is the inverse of f of x. The relationship with the xy coordinates is if you know -7, 4 lives here, then flipping those values, 4, -7 will be here. So that's the relationship of the coordinates. Boom, done. What types of translations, if any, affect the domain of a logarithmic function? So if we look at a typical logarithmic function, in general, it looks like this, right? And so there's a hard stop for the domain. So usually if we take a typical logarithmic function, let's call it log of x, right? Just log base 10 of x. It's going to have some point where it crosses the x-axis, and then it's going to have some invisible vertical asymptote. Usually in this case, it's going to be at 0. So if we apply a translation, for example, where we shift it to the right by 4, that will affect the domain, right? Because now instead of going from 0 to infinity, it'd go from 4 to infinity. So shifting to the right, also shifting to the left will affect the domain. Likewise, if we shift it to the left by 4, now the domain would be -4 to infinity. And then last but not least, if we did a flip across the y-axis in particular, like if we flipped it this way, that could affect the domain, right? Now we're talking about -infinity all the way up to 0. Now, just to let you know, a reflection across the x-axis won't change the domain, right? Even if we went like this, it would still be a same domain from 0 to infinity. So these are the three ways: shifting left, shifting right, and reflecting across the y-axis. Done. Does the graph of a general logarithmic function have a horizontal asymptote? And I would say no to this, because if we look at our general logarithmic function, in general, the graph is going to look like this, right? It's going to go up to the right, and here there's going to be a horizontal asymptote. There's going to be a hard stop in the domain, but it's going to go to the right forever and ever, and it's also going to go up forever and ever, and here down forever and ever. So there is not going to be any sort of set horizontal asymptote, set function height, max or min, where it's going to stop. It's going to go forever this way and forever up. It's just the speed rate at which it goes up might drop off, but it's going to go up and up and up forever. So I would say no, boom, done. So for this one, we're meant to state the domain and the range. And the thing about the range is, for a logarithmic, once again, in general, right, it's going up and down forever. And this one, there's a couple of transformations happening, so we want to be aware of that. But basically, if we were to rewrite this as -x plus 1/2, we'll see that we kind of get two transformations. By the way, we can factor out that negative a little bit further, and this will really help us see the transformation. So now it's negative, and then it's x minus 1/2. So we see two things happening. First, we see a reflection across the y-axis. That's what's happening when you have a negative on the inside of this ln. So normally it would be going like this. Now we're talking about a reflection across the y-axis, and then we're shifting it to the right by 1/2. So then we're going to the right, like just a little bit like this, okay? So when we're talking about the range is still going up and down forever. So range is still all real numbers. That doesn't get affected. But what about that domain? That domain is now going to the left. So it's all values from -infinity, right? Going up to what point? And the point where we'd stop is 1/2. And we're not including 1/2. And this is going to make a lot of sense, because if you think about a logarithm, you can't take 0 or a negative number as an argument. So when does this hit 0? When x equals 1/2. And then when is it going to be greater than 0? Because we don't want negatives. When it's going to be less than 1/2. So imagine when it's 0, it's going to be 1/2. Negative 1/2. This is going to be 1 inside, and so on and so forth. So it makes sense the domain is -infinity to 1/2. That's how you do it. Done. So for this function, for range, we're really thinking a logarithmic in general is always going to kind of go up and down without bound, right? So it's going to kind of look like this. So my range is going up and down forever and ever. So range is all real numbers. Now when we talk about the domain, so we think about the domain as really, for these logarithmic functions, where can x not go? And we know that as an argument of a logarithm, this value has to be greater than 0, right? So we can start by finding our domain just by saying 4x plus 17 must be greater than 0. And then we can isolate for x. So we have 4x is greater than negative 17. X is greater than negative 17 over 4. So as we state the domain, again, it's greater than, it's not greater than or equal to. So we have that curve parenthesis negative 17 over 4 all the way up to infinity. Boom, done. So here we're meant to find the domain as well as the vertical asymptote. And the nice thing is that the two are kind of connected, right? So for the domain, we're talking about this argument of the logarithm always being greater than 0. So x minus 5 must be greater than 0. And then we just solve this inequality. X has to be greater than 5. So that's my domain. So my domain is everything from 5 all the way up to infinity. Now, when we talk about the vertical asymptote, it actually exists at the start of this domain restriction, right? So if we're starting at 5, that means it's nothing, the value will never, of x can never equal 5 or less than 5, which means that is the vertical asymptote. It's actually at x equals 5 when this thing zeroes out. So here's your vertical asymptote, here's your domain, boom, done. For this one, once again, we're trying to find the domain and the vertical asymptote. So let's start with the domain, recognizing that this argument has to be greater than 0. We can't take 0 or a negative as an argument for a logarithm. So that kind of defines the domain. 3x plus 1 must be greater than 0. And then we isolate 3x has to be greater than negative 1 as we subtract 1, divide by 3 like so, and we get x is greater than negative 1/3. So to put this into interval notation, it's everything from negative 1/3 off to infinity. So there's the domain. And the nice thing is our vertical asymptote actually has to do with this starting point, meaning our vertical asymptote is at x equals negative 1/3. So there's your answer, vertical asymptote, boom, done. So for this one, we're meant to find the domain and the vertical asymptote. So we're going to start with the fact that this argument for this logarithm has to be greater than 0. That is what is allowed for logarithms. So we know that 3x plus 9 must be greater than 0, and this is the definition of the domain, right? What does x have to be greater than for this to work? So we're going to subtract 9 from both sides. 3x is greater than negative 9, divide by 3, x is greater than negative 3. So this is my domain, everything from negative 3 to infinity. What about my vertical asymptote? My vertical asymptote is at x equals the start of this domain. So vertical asymptote is x equals negative 3. And that makes sense because the vertical asymptote is meant to be a boundary for x values. And we just said x has to be greater than negative 3. So there you go. Boom. Done. So for this one, we're going to start by finding the domain. And the domain derives from the fact that this argument for log has to be greater than 0. So x minus 3/7 must be greater than 0. We add 3/7 to the other side, or to both sides really, and we got x is greater than 3/7. So here we have a domain starting from 3/7, not including it because it says greater than. So that's why we have the curve parenthesis going up to infinity. Likewise, we can do our vertical asymptote. The vertical asymptote is at the start of this domain, which means the vertical asymptote is at x equals that initial value of 3/7. Now we get to the end behavior, and we sort of have two end behaviors. We first have our end behavior as x approaches this vertical asymptote, which is 3/7. And we're approaching it, of course, from the right-hand side because we said that x has to be greater than 3/7, so it can't be less than, so we're only approaching it from one side, which is the right-hand side. So that means, we're getting to smaller and smaller x values, meaning imagine when x is 5, then 4, then 3, then 2, then 1, then maybe 4/7, and so on and so forth. So this argument, as we approach the asymptote, this argument is getting closer and closer to 0. And if we remember what a logarithm is, it's saying 10 to what power equals this value. So let's imagine when we're getting into those small values, like not 2 0, but imagine a fraction of like 1/10, 1/100th, etc. The only way you get there is when this gives you a negative output, right? Log base 10 of 100,000 is 10 to the negative 5th, right? So this would be a negative 5. So what you see is as this approaches that 3/7, as x gets closer and closer to 3/7, we're getting closer and closer to an argument of 0, which means this is getting closer and closer as a function value to negative infinity. Okay, now when we get to the other side, as x approaches the end behavior to the right-hand side, meaning as x approaches infinity, as it gets bigger and bigger, this argument's going to get huge, and as we take logarithms of larger and larger arguments, the function value is also going to go towards infinity. So there's the end behavior, there's everything done. So for this one, we're going to start with the domain, which is basically saying that this argument for the logarithm cannot be 0. It has to be greater than 0. So we start with that. We subtract 6 from both sides, and then we divide by 2, and we get x is greater than -3. So not only does this give us a nice domain, meaning we're going from -3 to infinity, it also gives us the placement of the vertical asymptote, which is right at that boundary, which is x equals -3. So that's that nice vertical line, and the domain is everything to the right, right? And it's kind of cool because you can immediately see with the typical logarithmic function, as we have our vertical asymptote with no reflections or anything like that, it's going to look like this, okay? And this is enough information to really give us the end behavior, because we can see that as we approach this line of x equals -3, this vertical asymptote, where is the function going? It's going down. So we can already say as x approaches -3, again from the right, because it doesn't exist to the left. So as we approach it from the right with that little plus, we can see the function value is going towards -infinity. And that's cool. That makes sense. What about the end behavior as the function goes off to the right, meaning as it approaches positive infinity? Well, this diagram seems to indicate that we're going up and up forever, which means that as x goes to the right or approaches infinity, the function is going to approach positive infinity as well. So there's your answer, done. So for this one, we're going to start with the domain and range. And again, the domain is determined by when this is going to exist, when we're going to have viable options for a logarithmic function. And that is only doable when the argument is above 0. So we already have this limitation that x minus 1 must be greater than 0. So here we're going to add 1 to both sides. X is greater than 1, which means the domain is everything starting at 1 going to infinity, but not including the 1, because we are saying it's greater than 1, hence the curved bracket. Now, when we talk about range, we think about any logarithmic function is going to go like this, right? And that's assuming there's no transformations or things like that, reflections that are going to change it, but it's not. It's your typical function logarithmic like this, down to the left, up to the right, and so that is going to go off indefinitely, so hence it's everything from -infinity for the function value up to positive infinity. That's going to go up and up and up. So there's the range. You could also write all real numbers. Now, when we talk about the vertical asymptote, we're going to go back to the start of the domain, which is at 1, and that also defines the vertical asymptote at x equals 1. Now we want to find the x and y intercepts. So the y-intercept is when x is 0, right? So look, we can't plug that in. There is no y-intercept because we already know that x, the domain of x has to be greater than 1, so we can't plug 0 in for x. So hence, the y-intercept does not exist, so we'll say DNE for the y-intercept. Now, what about the x-intercept? That's when this equals a function value of 0. So let's plug and chug and let's solve. So first, we're going to subtract 1 from both sides. I get -1 equals log base 4 of x minus 1. Then we're going to write this as 4 to the -1 power equals the argument inside. I'm converting it to exponential. 4 to that as a power equals that argument. So then we have this, and then I'm going to add 1 to both sides. And by the way, 4 to the -1 is really 1 over 4 to the positive 1, aka 1/4. So 1/4 plus 1 is 5/4, which means our x-intercept is occurring at 5/4, comma 0. So there's your answer. For this one, we're going to start by finding the domain, and that's dictated by this logarithm function. And it's dictated by this because in order to take a logarithm of a value, you can only take a value of 0, greater than 0, basically, right? Which means this argument, -x, must be greater than 0. And then as we isolate, meaning divide both sides by negative, it flips the inequality, and that means x has to be less than 0. So the viable options for x, or the domain, is everything from -infinity going up to, but not including 0. And this is cool because this also gives us the location of our vertical asymptote, right? Since 0 is the cutoff, our vertical asymptote is going to be at that cutoff of x equals 0. Now, if we talk about the range, you notice that typically a logarithmic function will go like this. But when you apply a negative inside to that x value, that's a reflection across the y-axis, meaning it'll kind of flip like this. So I'm just showing you to illustrate what this will look like, and we can kind of glean what the range will be. You see, there's no stopping to how far it goes down. There's no stopping to how far it goes up, which means the range is everything. It's all real numbers, or you can write it as -infinity to infinity. Now, when we talk about a y-intercept, remember a y-intercept occurs when you plug in 0 for x, but the problem is is that the domain does not include 0. We said that x has to be less than 0. It can't ever equal 0. And that means, by definition, that the y-intercept cannot exist or does not exist. And for the x-intercept, what we're going to do is we're going to plug in 0 for the function, and we're going to solve for x. So first I'm going to add 2 to both sides. We get 2 equals ln of negative x. Now I'm going to convert this to its exponential equivalent, remembering that natural log has a log base e. So we say the base to the power on the other side, e squared, equals negative x. Divide by negative 1. X equals negative e squared. So we can say our x-intercept occurs when x is negative e squared, and of course y is 0. That's the definition of an x-intercept. So there are your answers. Boom, done. For this one, we're going to start with the domain, which is everywhere that x can and cannot be, really. So we're talking about a logarithm and taking x as an input. Well, logarithms cannot take anything that's negative or 0 in, which means that this input x must be greater than 0. And there's nothing to really isolate. This is it. This is the domain, which means my domain is from 0, not including 0, hence the curved parentheses, all the way to infinity. And for my range, well, it's a typical logarithmic function that just kind of goes up to the right, down to the left as it approaches that vertical asymptote, which means that my range is all real numbers, hence negative infinity to positive infinity. We also get the vertical asymptote just from finding the domain. It's right here at that starting point, which means the vertical asymptote is at x equals 0. Now if we're trying to find the y-intercept occurs when x equals 0. But the problem is 0 is not part of our domain, which means by definition there cannot be a y-intercept. That does not exist. For the x-intercept, however, we need to just set the function value to 0 and solve for x. So first I'm going to add 9 to both sides. I get 9 equals 3 ln of x. Divide both sides by 3. And then we get 9 divided by 3 is 3 equals ln of x. Now we're going to convert it to its exponential equivalent. It's taking the base of this natural log, which is e to that power 3 equals x. So there's my answer, which means that the x-intercept occurs at e cubed, comma 0, right? Because every x-intercept has a y value of 0. There you go, done. So for 27 and 29, we really need to do all of these because we have to look at the comparisons between these different logarithmic functions to understand what's what. So we kind of have to do them all together. Now, when we're starting, what you'll notice is all of these have an x-intercept of 1. So that doesn't help a ton. But now we can look at the difference in the bases, right? When there's no base, this is a base of 10. For ln, it's a base of e. And then we have 2, 5, and 25. So we can kind of see the ordering in which these are least to greatest, by the way, right? E is 2.71 or rounds up to 2.72 as the base there. Then we have 10, 2, 5, and 25. So one way to think about this is as we're ordering based on these powers of the bases of the logarithms, let's compare 25 and 5, for example. Let's say that we have 25 taken as an argument for both of these, okay? So remember that log base 5 of 25 is asking the question, 5 to what power is 25? So for this one, it'll equal 2, right? So for a particular x value, this is going to be 2 when this is only going to be 1. You see that? Because 25 to what power is 25? This is the first power. So the trend that you notice is the larger that this is for a comparable x value, for the same x value, the output's going to be bigger for the smaller value, which means that since this is the smallest of all of them, this should be the highest up there. This should be the biggest. And this kind of makes sense too because we can check with A, which is the going up at the fastest pace. We see this point. This is at when x is 2, we get 1. This makes a lot of sense because if I plug 2 in, I'm saying log base 2 of 2 means 2 to what power equals 2? It's 1. And that lines up with 1 there. So we can see that 28 is A. And then we can kind of go in order, right? You can see that since A is the tallest, then B is the next tallest, which means it should be the next smallest base, which is E. So number 27 is B. Then we go to C. So what's the next smallest after 2 and E? That would be the 5. So C, so 29 is C. Then we get to D and E. Obviously, E is the lowest down, so that's going to have the biggest one. So that's 30. E is 30. And that means that 26, therefore, must be D, right? Because that is in between 25 and 5 for the base. So just to put it in a little clearer order, 26 is D, then we got 27 is B, 28 is A, 29 is C, and 30 is E. Boom, done. So for this one, we're going to look at all three of these simultaneously in order to figure out what's what. Now, what you notice is that for C and B, we're kind of inverted. We're not going the normal way, right? A is more of your typical logarithmic function. And what that means is that A is going to be paired up with 32 because we have a base that's greater than 1. So this is our typical log base 2, log base 3, log base 10. It's going to look like this, okay? And it also matches up with that nice vertical asymptote at x equals 0, though all of these are going to have that vertical asymptote. Now we're going to look at 31 and 33. So I'm going to look at 31 first. So this is log base 1/3 of x. Now the reason why this one is really helpful is because we can start by saying, well, I know that if I plug in 1/3, right, which is the same as the base, that's when we're going to get a function value of 1, right? 1/3 to what power is 1/3? It's 1. So 1/3, it looks like on the x value, it looks like, let's say right around here, right here. So which function is giving a value, an output of 1 right around 1/3? It sure looks like B. So B is our answer for 31. Now, if we look at 33, it must be C. I'm going to show you how to verify this. Once again, we have a base of 3/4. That means when I take as an argument for this logarithm, I take 3/4 as an argument for x, it should equal a function value of 1 because 3/4 to the first power is 3/4. So let's look at 3/4. That looks like it's occurring right around here. And look, that matches up with 1 for the curve of C. So I feel like that verifies that we've got C. So 31 is B, 33 is C, boom, done. So for this one, we're meant to sketch both of these on the same set of axes and kind of compare them. So I'm going to do the first one in black. And by the way, both of these have a vertical asymptote at 0 because you can't take 0 as an argument. It must be greater than or equal to 0. So we're going to put that vertical asymptote right here. And then I'm going to place log base x in black. And we're going to choose a couple of points to do this. So first, I know that when x is 1, this is going to be a function value of 0. That's going to be the x-intercept. That makes sense because it would be saying, again, there's no base written, so it's a base of 10. This would be saying 10 to what power is 1? 10 to the 0th power. And then what about when x is 10? That would be saying 10 to what power is 10? That's 1. So we got like 2 nice points right here. And then as a typical logarithmic function, we can see that it's going to kind of go in this direction, up and up and up forever. And then as we approach that vertical asymptote, it's going to kind of hug it and go down. Now we're going to talk about this one, and I'm going to do this in red. So it says log base 1/2 of x. So again, we're going to get a couple of nice points. Once again, when x is 1, okay, that's going to be 1/2 to what power is 1? Well, that's 1/2 to the 0th power. So again, when we plug in 1 for x, we get a nice x-intercept. But now let's plug in 1/2 for x, right? That's when the argument equals the base. 1/2 to what power is 1/2? That's the first power. So when x is 1/2, we're all the way up here at 1. So that's interesting. And that makes sense because with this argument being between 0 and 1, we should expect it to be something like this. But now we're going to get a couple more points. When x is 2, 1/2 to what power is 2? 1/2 to the -1, right? 1/2 to the -1 power equals 2. That means when x is 2, we got a function value of -1. Now, just for fun, we're going to plug in 4 for x, okay? So when you have log of 1/2 of 4, right, what does that equal? So again, this is saying 1/2 to some exponent y equals 4. Well, that's going to be to the -2 power, because if you plug in -2 for y, 1/2 to the -2, that's really taking 2 over 1, the reciprocal to the +2, which does give you 4. So when x is 4, we got a value of -2. Now this gives us enough information to really plot this out. So we can see kind of goes down, whoops, like this, comes around and goes out like that. So you can see it's just flipped sort of like that, but that's how you would compare and look at the two graphs. Boom, done. So for this one, we're meant to graph both of these on this graph here. So first we're going to graph f of x equals e to the x, our exponential. And by the way, these are both inverses of each other, if you didn't notice that, because this is e to the x, that's logarithm base e of x. Well, anyways, let's graph this one first. Our typical exponential, we should expect it to go like this. But we know that when x is 0, e to the 0 is 1. When x is 1, e to the 1 is e, which is roughly 2.72. And when you have -1, e to the -1 is 1 over e, which is about 1/3, a little bit above 1/3. So we got some stuff there. And by the way, we also have this nice horizontal asymptote at y equals 0. That's our typical one for an exponential equation like this. And that makes sense. As x gets super, super negative, this gets close to 0, but it never goes negative. So we can see it hugging that vertical asymptote here and then kind of shooting up like this. Now when we come to ln of x, let's do that in red. And again, a typical logarithmic function is going to look like this. And if we've done it correctly, it should look symmetric to e to the x across the line y equals x, that diagonal line. So let's just plot a couple points. Let's see how it looks. So first of all, I know I'm always going to start with ln of 1 because a log of 1 is always going to equal 0, right? So that means when x is 1, we've got this nice x-intercept here. We also know that since this is log base e to what power is e, right? So that means when I'm plugging in e for x, I should get 1 because e to the first power is e. So 2.72 roughly for x should give me a function value of 1. And we can also think ln of 1 over e, which is the same as ln of e to the negative 1. This is saying e to what power is e to the negative 1? Negative 1. So what does that tell you? That tells you when you plug in 1 over e in for x, which is about a third, then you're getting a value of negative 1 for the function value, so something like this. So you see these points kind of mirror these 3 points there. And by the way, since we do have this natural log of x, x cannot be 0 or negative, which means we have a vertical asymptote there, and then we kind of hug the asymptote as we go down. Hug this vertical asymptote as we go down, and then shoot off like this to the right. And there you have it. So there's ln of x in red, there's e to the x in black. That's how they look together. Done. So for number 39, we're trying to figure out whether a, b, or c match up with this graph. Now, the thing I can tell you, first of all, it's a typical logarithmic function is going to look like this, right? But then we've negated in the front. So when you throw a negative in the front, what's going to happen is you're going to flip it across the x-axis, meaning now it should look like this. So on this basis alone, if it's supposed to look like this, we know that C is the only option. It's got to be C. But just for confirmation, I'm going to show you a couple other points that's going to verify that C is correct for 39. So for example, when I plug in 0 for x, we'd say log base 4 of 0 plus 2 would be log base 4 of 2. So log base 4 of 2 is asking 4 to what power is 2? That's 4 to the square root, or 4 to the 1/2 power. So that would give you 1/2. And then you negate that, and you get negative 1/2 when x is 0. Look at that. C, negative 1/2 when x is 0. Another easy point to verify is plugging in 2 for x. So if I plug in 2 for x, I get 2 plus 2, which is 4. Then I have negative log base 4 of 4. And this is nice and easy because when you have a base of 4 and you're taking an argument of 4, that's always going to cancel out to 1. So that means when we plug in 2 for x, we get negative 1 for y because of the negation in front. That's also on C. So there's your 2-point confirmation. C is the answer. Done. So for this one, we're just meant to graph this function, log base 2 of x plus 2. So the way I'm going to start is I'm going to start by trying to take log of 1. So that, and we'll make a little table of values. That's going to be when x is negative 1. When x is negative 1, we're taking log base 2 of negative 1 plus 2, which is 1. And remember, log of 1, regardless of the base, is always going to give me a function value of 0. Okay, so that means when I plug negative 1 in, I'm taking log base 2 of 1, which is 0. Another great place would be plugging in 0, right? Because if I plug in 0, now I'm taking log base 2 of 2. And another shortcut that I mentioned earlier is when the base and the argument are the same, the output is 1. Another way of saying this is 2 to what power is 2? 2 to the first power is 2. And then we can do one more maybe when x equals 2. Because when x equals 2, that's another nice point because then we're taking log base 2 of 2 plus 2, which is 4. And I like that. I like powers of the base because this says 2 to what power is 4? Well, that's a nice whole number of 2. So now I got 3 really good points. The last thing I'm going to say is, where's my vertical asymptote? Well, that's going to be when this argument zeroes out because we can't take 0 or negative numbers, which means it's going to zero out at negative 2. So we have a vertical asymptote at x equals negative 2. So there's my vertical asymptote. And then with these 3 points, we have negative 1, 0, we have 0, 1, and then we have 2, 2 like this. And then if we're to plot this out, it's going to look like this. It's going to shoot off up like that. And then here it's going to shoot down, but it's going to hug that vertical asymptote. So there we have a great graph. Boom, done. So for this one, we're graphing ln of negative x. So I can show you how to get a pretty quick rough sketch. When we typically have ln of x, it's going to look something like this, right? Just approximately. Now, when we negate that inside x, that's a reflection across the y-axis. So I can already tell you that it should look like this. Now to get a little bit more precise, we're going to plug in a few points. So like I said, I like to start with taking ln of 1 because ln of 1, I know that's going to be 0 because it's saying e to the what power is 1, that's 0. So what's going to give me 1 if I plug in negative 1 because we're going to negate it and it's going to take ln of 1. So I know that's going to give me an output of 0. I also want to see when I can take ln of e because that's always going to be when the base and the argument are the same, that's going to give me an output of 1. So to take ln of e, I need to plug in negative e because that's going to get negated to positive e. So negative e is going to give me an output of 1. And last but not least, just giving me one more option. If I plug in negative e squared, that's going to give me ln of e squared. And e to what power is e squared? That would be 2. So that gives me a third point. And what is e squared, by the way? It's 2.7 times 2.7 roughly. Okay, so that's approximately like 7.3. Okay, so this would be negative 7.3. So let's get these points here. So we got negative 1, 0. We've got negative e, which is negative 2.7 roughly, and then 1. And then we got this one, which is negative 7.3, 2 like so. Once again, for that vertical asymptote, it's where is this going to have a hard barrier? That's going to be when x is 0 or greater than 0 because that would mean then we'd be taking log of either 0 or something negative because of that negative sign. So here's our vertical. Now we can kind of connect the dots coming down this way, hugging that asymptote forever and ever, and then over here, going through this way, and there's our graph, boom, done. So in order to graph this one, we want to first recognize that that's really a log base 10, right? When they don't put the base, we assume it to be a base of 10. Also, with this negative in front of the x value, right? We already know that that's going to be a flip across the y-axis. So this just tells us a couple things that, you know, we're probably looking at something that looks like this. But now let's get a couple of nice points in here and let's see if we can get a decent graph. So I want to start with my horizontal asymptote and really the domain because that's going to occur when this is going to zero out because this argument has to always be positive. So we can say, when is this going to equal 0? Or really say, when is this going to be greater than 0? So we can now solve for x. Negative 3x is greater than negative 6. Divide by negative 3. X is, and we flip that inequality. When you divide by negative, x is less than 2. So that means my vertical asymptote is going to be at 2. And it's going to be everything to the left. And as I already mentioned, it should look something like this. But now let's get a couple points to plot it out. So since this is base 10, I'd love to get a value in here of 1 and then eventually 10. So to get 1, I need to plug in 5/3 because 6 minus 5/3 times 3 is 1. So when x is 5/3, we plug it in, we get 6 minus 5, which is 1. Log base 10 of 1 is 0 plus 1 is 1. Another place is I'd like to get this to equal 10 because when this equals 10, log base 10 of 10 is 1. So that's going to happen when x equals negative 4/3 because negative 4/3 times negative 3 is 4 plus 6 is 10. Log base 10 of 10 is 1 plus 1 is 2. And so now just looking at these 2 points, 5/3, that's 1 and 2/3 comma 1. We've got negative 4/3. This would be negative 1, 2, 3, 4/3 right here and positive 2. So we got those nice points, and then we already know that as this comes down, we're going to be hugging this asymptote. And then as we go to the left, we're going to be connecting the dots through here, and it's going to go up and kind of to the left. So that's how you do it. Boom, done. So for this one, we're taking this parent function and we're applying transformations to make it look like this. Now, just from the fact that we know typically a logarithmic function is going to go this way, we know that it's been at least reflected across the y-axis. So since it would normally go like this, reflecting it would now go like this. So this is how we would apply that reflection to the y-axis, a negative in front. And then you'll notice that we need an x-intercept, well, and a y-intercept of 0, 0, going through the origin, okay? So right now, this wouldn't fly, okay? Right now, negative 1 would be giving me the 0. So I need 0 to be giving me the 0, meaning I needed to be able to plug in 0 for x and somehow get 0 for this, which means if I plug in 0 for x, I should be getting 1. Because log of anything of 1 is 0, okay? Long way of saying I need to get a minus 1. And this also makes sense because if you see how I've drawn the graph, it needs a shift to the right by 1, and a shift to the right is by minusing 1 from x, right? Shift to the left, you'd be adding 1. And then last but not least, we'll exchange that y with f of x if we want this in function notation. So the f of x equals log base 2 of negative x minus 1, boom, done. So for this one, we're trying to take log base 4 of x into this function. So just so we know, log base 4 of x would typically look like this. So that's just a rough approximation. So off the bat, it looks like perhaps this has just been shifted 2 to the left. So shifting to the left, you'd actually add 2 like so. But the problem with this is that you can immediately see if I plug in 0 for x, I should be getting 1/2, right? 4 to the 1/2 power is 2. But here we're getting 1.5, aka 3/2. So there must be some multiplier in front of this that is changing the value. So we can now say like, okay, a log base 4 of x plus 2 is equal to the function. But in this case, let's set it equal to that 3/2. And then we're going to plug in 0 for x and solve for a. Now, the reason why I say it has to be a stretch versus a vertical shift up is because with this as the horizontal shift to the left, I don't want to shift this up because it's gonna mess up my x-intercept. So I'm gonna say this is the change that we're sticking with, and then now we're just gonna stretch it out. So we have 3/2 equals a log base 4 of 0 plus 2, which is just 2. And then, by the way, log base 4 of 2, as I mentioned before, is 1/2 because 4 to the 1/2 power is 2. So that means 3/2 equals a times 1/2, which means for this to be true, a has to equal 3. So then we get our final function equation, plugging in 3 for a, equal to 3 log base 4 of x plus 2. So there's your answer, boom, done. So for this one, it says use a graphing calculator to find approximate values for x. So what I'm gonna do is I'm gonna plug it in as follows. I'm gonna set one function equal to the left side, which is this, and then I'm going to set the right side as another function, ln of x minus 1 plus 2. And we're going to see where they intersect, and the x value of the intersection will be our solution. Okay, so as I graph these two, I can see where they intersect, and they intersect at 2, 2, which means x is 2. So 2 is the answer, boom. So to solve this using a graphing calculator, I'm going to set two functions, one equal to the left-hand side in Desmos, which is ln of x minus 2, and then for the second function will be what's on the right-hand side, which is negative ln of x plus 1, and we're going to just see where these two intersect. So we can see that these two intersect right here, and again, we're solving for x, so we're looking for that x value of 2.303. So x equals approximately 2.303, boom. For this one, using Desmos, I'm going to create two functions, one based on the left side of the equation, which equals 1/3 log 1 minus x, and then I'm going to use the right side of the equation, g of x equals that right side log of x plus 1 plus 1/3, and then what I'm trying to see is where these two are equal, aka where they intersect. So let's use Desmos now. So here we can see the two graphs. Let's see where they intersect, which is right here at an x value of negative 0.472. So the answer is approximately negative 0.472, boom. So what we're going to do is we're going to take a look at the graph of both of these functions in Desmos, and we're going to compare them. So as we graph the first one, we see it's this red line. And then when we plot the second one, negative log base 2 of x, look at that, it's right on top of it, which means that these two graphs appear to be identical, which means the functions are likely identical. So what this leads me to believe is if I take log of 2x, okay, and it's negative, what this seems to be equivalent to is it's almost like if I take this negative and I apply it as an exponent, like -1 for this, it seems to be the same. So for example, this is equivalent to 2 to the -1 of x, which is 1/2. So likewise, I would imagine negative log base 5 of x would be the same as log of 5 to the -1 of x, aka log of 1/5 of x. So let's test that out. So here we plotted log of 1/5 of x, and then here's negative log base 5 of x, and look at that, they're the exact same. So I think we verified that, and that's our conjecture, which means negative log base b of x is the same as log of 1/b to the x. There it is, done. So for this question, it asks, what is the domain? And again, we're going to go back to that basic idea that for a logarithmic function, the argument has to be greater than 0. So we're going to start with that premise that this has to be greater than 0. Now, when you have a rational expression greater than 0, the way you have to solve this is you have to look at both of the 0 points for the numerator as well as the denominator. So we can hit 0 here at -2. We can also hit 0 at 4. And then within this range, we have to see where is it positive or greater than 0. By the way, at -2, this would equal 0. So this is not a viable option. At +4, it would be undefined, dividing by 0. So that's also not an option. So we're excluding both -2 and 4 right off the bat from the domain. Now let's see when we have values less than -2, like -3. -3 plus 2 is -1 over -3 minus 4 is -7. The negatives would cancel out. That would be positive. So this is a good spot. In between -2 and 4, let's try 0, okay? So you plug in 0, you get 0 plus 2 is 2 over 0 minus 4 is -4. That's -1/2. That's negative. And we can assume, because these are the only crossover points where it goes from 0 or undefined, that it's going to be negative for any value in here. That would be -1, 2, 3, all of those. So you can plug them in and try them and verify that, but I'm pretty confident, so we're going to move on to values greater than 4. Let's try 5, for example. 5 plus 2 is 7 over 5 minus 4, which is 1. That's 7 over 1. That's positive. So I'm going to assume that every value greater than 4 is going to be a value that's going to be greater than 0, which means that's part of the domain. So this is now my domain, my viable domain. So I can write this out as everything from -infinity. So I can write this out as everything from -infinity up to, but not including -2. So we have a parentheses like that, curved, not including. Also joining or unioned with starting at 4, but not including 4, hence the curved parenthesis going to infinity. And there's your domain, boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.